And what I'd like to really get through today is 9.1 and part of 9.2. Let's talk about center of mass first. Let's talk about why it's important. So up until this point in time, anytime we've had a force applied or we've had motion of an object, we've considered that object to be what? Not a full object, but instead a particle, a point in space, very good, particle. So we've considered that all that mass has been concentrated into this one little location. And as a result, if we have that one little location with a force applied to it, which we're drawing with the dot, we know the way the entire thing will move. But in reality, systems are not made up that way. So for an example here, if you had, let's say, oh, here we go, here's a good one. We have recently for the Science Olympiad project, the students made like this gravity vehicle that had to go down this ramp. And the way the vehicle worked was as follows. There was like a metal perimeter here. Then there was a lot of mass in the corner. Then there was a lot of mass in this corner. And there was a metal piece here, and heavy mass here, and a heavy piece of mass here. These were connected with metal struts, and the same here. Now, even though this was metal on the perimeter, this was actually aluminum. It was really light, very low density metal. So most of the mass was concentrated in the corners, actually, where they came together, where there was bearings and where there was a 3D printed element. And then there were also wheels on this car, and those wheels were located like here, 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 and here. And then we had axles going through, and those axles are pretty lightweight. But that was the general shape of the car. Now, if I look at this gravity vehicle or this car, whatever it is, just because of the symmetry involved, where will the center of mass be in this example? Because of the symmetry involved. Smack in the center. Now, what's interesting to note, though, is that there's nothing there in the center. It's empty space. And I'll pull it out so you guys can see what I'm talking about. But the idea behind center of mass is that the center of mass of an object where the masses are all distributed doesn't actually have to be the center or part of the object. So this is what it looks like. Okay? So that's what I was trying to draw in this orientation, though. The wheels in the top bottom, these are the axles, these are these metal pieces, and this is where a lot of the mass ended up becoming. Then we had the actual bearings there. But the center of mass of this will most likely be here, which is not actually part of the object, right? So what we notice is that the center of mass of an object doesn't actually have to be part of the object itself. So in this circumstance, it's smack in the center there. Now, what if suddenly, on the back of the car, you put a lot of weight, right? Let's indicate a lot of weight with this green here. Let's put a green mass here in the back. What if we added a ton of mass only to the back of the car? What would happen then, Jeff, to the center of mass?
The center of mass would really shift towards the new mass to the back.
Yeah, it would shift toward the back of the vehicle in this case. So instead of the center of mass being here, which is where we said it was a moment ago, the center of mass might move now, and I'll use green. Maybe it moves to a location like right here instead, because of this suddenly concentrated mass on one part of it. And you've seen this before. You know this happens. Because if you step on something like a dolly, I wish I had a dolly in the room. Does anyone know what a dolly is? 4 pieces of wood with wheels on each corner to move furniture, right? Not the upright hand truck, but the actual dolly. It literally looks like, I'm seeing weird looks and faces. It looks like this.
Because if you stand on the back of it, it goes.
Yes. So put 4 wheels on a little dolly, right? That's what a dolly looks like. It's 4 pieces of wood attached. If you step on the very back of the dolly, what happens? It flops up, right? And it's flopping up like that because of the fact that you're now applying torque, really. You're causing rotation to it. But what you're really doing is you're greatly adjusting the center of mass of this. So suddenly, it wants to balance on a further point back, and now by you stepping like right here, now the center of mass is right here, instead of it being smack in the middle. So a distribution of even mass causes the center of mass to be evenly in the middle or evenly centered, and that's when we look for symmetry. But as soon as we have like an applied force right here, now that center of mass is no longer going to be in the middle, but it might be somewhere around that spot right there. Which is why the whole thing turns up a little bit, and that center of mass is the only spot that's balanced. How do I find, maybe you guys know this, this is a fun one. How do I find the center of mass of any lengthy beam? Yeah, you try to balance on one finger. So I do this. Is it going to balance? probably with my finger.
6 inches.
Yeah, probably in the middle of the 15 centimeter mark or the 6 inch mark. And if you're ever wondering if something is not, because this one is evenly distributed, the mass, but if it weren't, just go like this with your fingers. They'll always be in the center of mass. Try it. It's a weird one, actually. I'll pass around a couple of meter sticks maybe so you can see it a bit better. It's actually really weird. Take your finger. Did you guys do this last year at all or not?
No,
I don't know. I'm trying to think if I did it in my class last year. I'll give you a couple of meter sticks. I'll pass them around here. So go ahead and do this real quick. You try it. The person next to you try it also. Take your fingers. Just put them in arbitrary distances, but make sure they're all the way out. Yeah, start all the way out. Just bring them together. Start them all the way out and simply just bring your fingers together. Look at where they meet. It's always going to meet at the center of mass. And you're not even trying to do it, whether you realize it or not. You can only try to only move your right hand first. Like literally, try to only move your right hand for a little while, and then eventually you'll have to move your left hand. Isn't it weird? Where are they all meeting? They're all meeting smack in the center. They're meeting at the 20-inch mark. It's about 40 inches. So, let the person next to you try also. The person next to you try it out. Maybe you guys will. It works. So you start them. So what you should do is start them at not even points, but don't put them both on the same side of the 50 mark, or else it won't even match, right? But start them one on each side at different locations on purpose, and then start sliding your fingers together. You'll notice they'll slide together at separate rates, and it kind of messes with your head. If you start them both evenly, then they'll kind of both evenly go, but you'll notice, look, I'm not doing this on purpose. One finger's moving and then the other's moving. There's definitely friction involved, absolutely.
Like, because if you move this one more and more, there's less weight on it, so then this one
has to compensate for that?
Yeah.
And that's what you're doing.
Oh, yeah.
It's a weird thing. Your fingers start moving, and you're like, I'm not even doing this. I'm trying to push both together, and yet only one finger will move, and then only the other will move. And you're not actually controlling it yourself. So the center of mass at the 50 mark, here's another way to find center of mass. There's a doctor taught me this one the other day. This is pretty cool one. I never tried it. You can take something like this, right? And you can continue to push it off the desk. And it won't topple until the center of mass is beyond the edge of the table. So look, I'm at 49 centimeters, and it's just still not moving. I'm at 50 centimeters, and watch, look, do you see it? What's happening? Look, you see it's kind of like starting to jump up a little bit? Now this ruler has a little bit of tape, so maybe it won't be perfect. Look, there, see it happening? See how it's starting to slightly come off the table there? If I go back even a little bit, it's going to fall. So now if I go a little bit further, there it goes. So you can find the center of mass of any object by just sliding it off the table. So this is only a one-dimensional object. I know it's two-dimensional, but because it's symmetric, we're going to say it's only a one-dimensional object. But what if instead, what if we had something like this object here? We wanted to figure out its center of mass. Well, we've got a couple calculations to make. We need to know where the center of the mass is this way, and where the center of the mass is this way. So we have to start by pushing it this way, and when it's about to fall, we can mark off that location, okay, about the center of the mass, so it's not perfectly between the two. And then, so that would give us the center of the mass this way. But then if we want to find the center of mass this way, we have to go like this now. We start to push this side. And keep going, keep going, keep going. And there it goes. And it's about where you expect. It's about halfway between this direction. So the direction that you're trying to find the center of mass in, push in that direction. So if you're trying to find the center of mass this way, you push along that direction. If you're trying to find it this way, push along this direction. And as soon as it's about to tip over, you're at the center of mass. So center of mass is not a one-dimensional thing, yet two-dimensional. So this center of mass would be pretty much here when looking from above. And in this direction, we can find the center of the mass by suddenly turning it and doing this. And keep pushing and pushing and pushing, and eventually it falls. So the center of mass of this, you would expect where it is, because it's a regular hexagonal prism. So it's going to be right there in the center, right in this center, and smack right in the center there. So this is an empty space right in the center of this entire thing. That's where the center of mass is. Just like one other shape, where the center of mass is always in the center of the object.
Circle.
Not specifically circle.
Square.
What is it?
Sphere.
A sphere. A sphere. Three-dimensional, right? So what are we talking about? We're talking about shapes here, three-dimensional. But a circle would be the center, two-dimensional. The center of a circle. Again, though, this assumption is that what? The material is the same throughout. There's a word for that in physics or engineering. It's called isotropic. An isotropic material means that its physical properties don't change based on its location in the solid. So it doesn't suddenly become more dense. What would be an example of something that has variable density? It would be like this, some part of a door. This is not isotropic at all. This material is different than this material, and there's a concentrated mass over here, and it's not over here. This is a different density, or this metal, which is different than glass. So this would not be a system in this case that is isotropic or the same throughout. On top of the fact that this is obviously a concentrated load right here, or a mass. But even the material properties, I'm saying, are changing throughout the solid. So this example is a good one to start with. It's a good one to start with. But let's take a look at an example where we don't have equal masses. Okay, we don't have a distributed mass. So let's start with this one first. If you were told that an object was here at the location of 2 meters and another one at the location of 8 meters, and I put them simply on the x-axis to start, and I told you that the masses were identical, then what's the center of mass in this case? If the masses are identical, it's going to be 5 right down the middle. Be careful. 5 right down the middle there. So 5 would be the center of mass for this if the masses were identical, right? If they were identical. But what if suddenly this one had double the mass that this one has? Which way would the center of mass shift? Which way would the center of mass shift?
More towards the 8 meters.
Correct. More to the right in this case, or toward the 8-meter marking. I agree. The center of mass is no longer going to be located at the 5-meter mark, but instead it's going to shift slightly to the right. And we'd all agree because the mass is concentrated toward the back. The question becomes, how do we figure out that exact location? How do we figure it out? And what I want to, give me one second, Chris. What I want to show you is what I think of it as called a weighted average. It's like a weighted average. And here's what I mean. If I asked about the average in this class, right, and I talked about a specific quiz or test or whatever it may be, and I simply said, well, you know what? The average for the boys in this class was an 85, but the girls got an 88. Can I just say that the class average is the average of 85 and 88? Is that reasonable to say that? Why not? There's more guys in the class, right? Oh, hey, look. Same concept. There's more mass here, so the average or the center of mass should be leaning toward the heavier mass. Just like, if, again, the boys had an 85, the girl had an 88, the average would probably be closer to an 86, not an 86.5. Right? Logically? It's the same concept here. So the center of mass is like a weighted average of all the distributed mass that are occurring in the problem. So what we do is we do the following. We use a formula. This is called the center of mass formula. COM, you're going to see a lot in your textbook. And they write it as lowercase COM. And when I was reading the book 3 days ago now, Friday or Saturday, I was reading it as COM at first. I'm like, why do you keep writing COM? And I realized they're referring to center of mass over and over again. But they don't use dots, they don't use capital letters. They're going to write the lowercase word COM. And you might not necessarily pick up on the beginning. They're talking about center of mass. So the center of mass of any particle is really going to be the mass of the object times its location, plus the mass of the second object times its location, all over the mass of the objects summed together. Now I'm writing a non-mathematical expression here. How might we write this mathematically? What symbol have you been using in calc to represent several things added up over and over again? Sigma. Very good. So this is really going to be sigma. So the center of mass is really the summation of all the mx's where I goes from 1 to k over the sum of all the masses. So M1, X1, M2, X2, M3, X3. However many masses we have. So up to K masses. So I'm using for K up here. Now, the concept I want you guys to recognize is that what are we really doing? We're looking only in one dimension first, then we can look at the second dimension, then we can look at the third dimension. So this is the center of mass for the x-coordinate, really, because I'm using x for my position. So if I were finding the center of mass vertically, in this problem, it wouldn't move because there is no object above or below the axis we're on. But if suddenly, let's say I put the object here, look, another one right there, and I call this 1/2 m. Well, now the center of mass is definitely not going to be on the horizontal axis anymore. It's going to shift upward, and it's probably going to shift slightly, to the right. So the center of mass might now be, like, I don't know, over here maybe? And again, I'm estimating when I'm drawing these x's right now because we're not calculating just yet. We will definitely calculate as we get values and numbers. But I want you to see how the center of mass shifts either left to right or up or down based on the introduction of a new mass in the system. There's some new mass in the system. Does this make sense, the idea? It's a weighted average, So we're going to continue to use this formula here, which is really, again, this formula right here. Let's look at an example to see this a bit better. The example I want to start with is on page 217. Okay? And on page 217 it says the following. 3 particles given a certain masses form an equilateral triangle with an edge length of 140 centimeters. Where is their center of mass? Where is their center of mass? So we've got 3 different masses and they form an equilateral triangle. I'm trying my best to draw an equilateral triangle. That's not good. It's kind of better. And what we notice here is that the masses are given as following. The bottom left one is given as 1.2 kilograms. The top middle is given as 3.4 kilograms. And the bottom right is given as 2.5 kilograms. We're told that the edge length of the triangle, or the side length, is 140 centimeters. And the question is, where is the center of mass? So, let's start by obviously answering the question, if the masses were all the same, where would the center of mass be? Right in the middle. Okay, smack in the middle there. We would average out these coordinates, and we would then figure out this one. Now, smack in the middle here, really in this case, we know that it's going to be leaning which way? Where would the center of mass end up being? Compared to where it would start if they were equal mass. And? Good. It's definitely going to be up and to the right. Again, it's got to be up and to the right because the mass in the bottom left is the lowest of the masses. So it's going to have the weakest pull in a sense. It's not like a gravitational pull, but I'm talking about, like I said, I use the word pull. I don't use the word force. But this has the least impact on the answer and the other two do. Max?
Does it depend on the fluid that the object is in?
The assumption for anything is that we're in air right now.
But does it, because in water it's easier to balance?
Oh, but the center of mass doesn't change, no.
Okay.
Yeah, if you're suspended in water or, I don't know, molasses, thicker versus air, center of mass isn't going to change its location.
Okay.
Now, if there was buoyancy and the buoyancy caused it to be above the surface, then you could have some issues of where the force applied from and how torque would apply. But yeah, in this case, we're assuming everything is going to be in air. It's not going to be in fluid. Chris, you had a question earlier. I never got to it. You got it? You answered it? Or I answered it? It's my turn. So when we think about this problem, we want to think about their locations. So locations are really important. So what do you think I should probably draw for this example? What should I probably draw in here if locations are important? Yeah, some sort of a grid line or a graph. So to make life easier on us, you probably, and I would highly recommend it, want to put one of these masses where? Where would one of these masses make it useful?
Put it along the x-axis.
Good. More specifically? You said put it on along the x-axis, Chris? at the origin specifically. And let's talk about why that is. So let's go ahead and introduce a y-axis here and an x-axis here. Why the origin, Chris? Any idea why the origin there? How's that going to help us? Or anybody else, honestly? Why the origin? How is the origin going to help us? Think about our determination of center of mass. How do we actually get the center of mass? How do we actually get the center of mass? Yeah.
Mass times position. So if the position is 0, the mass just can't 0.
It drops off. Yeah, really good there, Matt. So the concept of center of mass, remember the center of mass in the x direction is again a weighted average. It's the mass times its x position plus the mass times its x position plus the mass times its x position. Oops. All over the sum of the masses. Notice I'm not converting units here. I don't need to. I'm finding a location. Everything's given in centimeter mass, so just be in centimeters. I can convert that at the very end if I want. But the center of mass along the x direction, think about it. You're just looking at the x-coordinates for each of these. The x-coordinate here is 0. The x-coordinate of 2.5 is 140. The x-coordinate of 3.4, well, that's halfway across the triangle, right? That's why I got 70 pretty quickly here. Because it's halfway across the triangle. That's where the 70 comes into play. The y direction is a little bit trickier. The y direction is a little bit trickier. What do you got?
I have a question.
Yeah.
So where do we draw the origin usually? Just usually like whichever point is from?
It would make sense to make one of your masses, if you're given several masses, at the origin. And then the others are from there. So I could have, Carol, made this the origin, and then the other mass would be on the left side. And that's fine also. Okay, but then my center of mass would have a negative x location, which is fine, which means it's to the left of the origin. How would the y direction look? Again, we take the mass times the y value, the mass times the y value, the mass times the y value, all over the sum of masses. Chip, what are you thinking?
But the distance is going to be different. You're not given the distance.
For what?
Y-axis.
For
the y distance for the 3.4.
Okay, so give me the other two. What are those?
0.
Yeah, so we already have 1.2 times 0, because that's still at the origin. 2.5 times 0. I agree. And then Chip makes a good point. We don't know what this height is right here. We know that all the masses together is going to be this, but we're still missing that height that's left blank there on the far right. Got it?
Wouldn't it be times root 2? I forget what the number is. But
I know, right?
45, or 90.
30, 60, 90.
Yeah, 36.
Let's drop down a, what is this called?
Axis of symmetry.
Oh, that works. Okay, axis of symmetry. What else? What's the other word for triangles? What do we drop down a what? Altitude. Let's drop an altitude here. In this case, altitude or height are the same because they're both going to be splitting the base, right? We're talking about, median or altitude is the same. They're splitting the base and they're perpendicular both. But the question becomes, what is that length of that dotted red line there? So this angle, remember, is 60 because it's an equilateral triangle. This makes that 90, which leaves this as 30. We know that this length is 70 centimeters right here because the entire length was 140. So you could do this, 6, 7 different ways to get the answer. You could use Pythagorean theorem, you could use sine and cosine, you could use tangent, sine or cosine or tangent. So you can use any of the three trig functions or Pythagorean theorem, whatever you want to use. Get the height of this triangle. I personally am going to recognize that, you know what, this is 140. And I could say if I want the y value, I could say 140 times the sine of 60. That'll give me that y height that we're talking about right there. Okay, again, think about like this is the vector length, 140 times the sine of 60 will give me the vertical component. The horizontal component is 70 because what's the cosine of 60, everybody? What's the cosine of 60? What is it? 0.5. And what's 0.5 times 140? Gives us back to 70. But if I want the vertical component, I have to take the hypotenuse times the sine of the angle here. So what is that going to give me as a value? I know it's radical 3 over 2 is sine of 60. But what's radical 3 over 2 times 140 going to yield? Chip, what does it become?
What'd you say?
What does it become, this answer up here? I thought you were doing it. 156. 56? It's got to be less than 140, right? 140 times the sine of 60. Are you in radian mode, degree mode? It shouldn't matter. Shouldn't matter.
Oh.
Even if you're in radian mode, you're still sine of an angle should be less than 1. Can you check it again? 140 times the sine of 60? 121.24.
Yeah, I plugged that in and I just got negative 42. I'm in radian mode right now.
You are in radian mode, but that still shouldn't have given you an answer of 150 something, you know?
No,
You can never go
I
up.
plugged that in and now I got negative 42.
So you're currently still in radian mode,
I
probably.
just changed it, so if I did that,
So then re-enter it.
then it's 121.
Okay. So this height is going to be 121.24 right there. Again, that's the y value. I don't want you to get bogged down in the trig, unfortunately, because honestly, the trig should be like, right? It should be second nature. You learn trig in 10th grade, which is why by senior year, your trig should be down pat. So I don't want you to get bogged down on that. What you notice, though, is that the y coordinate of this guy up here is 121.24, which is what we plug in here. The y coordinate of the other two was 0. So those have no effect on the center of mass because they're technically along what's called the 0 line. So what do we get for these two answers? What do we get for these two values? There's going to be some calculations involved here.
The first one was like 82.
82.
Yeah, it's 82.82.
0.82. Thank you. So I'm rounding to the nearest tenth for right now. So take a look at our answers. Max, you answered earlier. Do these answers make sense?
Yeah,
Why?
because the X one is. Oh yeah, it's a little bit past halfway.
Because halfway would be?
70.
So this
and
is
then-
beyond halfway. Okay, I'm with you. Keep going.
And then the halfway to the top would be 60, but since there's 3.7 kilograms on the bottom part, then it should be slightly towards the bottom.
Okay, so you would recorrect your statement from earlier then, wouldn't you?
Yeah.
And I agree with you earlier because when we think about comparing it to a normal triangle, we'd say, oh, well, look, suddenly there's a high concentrated mass at the top, right? But the overall value of these two at the bottom is greater than this guy at the top. See what Max is pointing out? That these two sum up to be 3.7 kilograms at the bottom? So there's more of a pull toward the bottom for center of mass. So this is going to be slightly less than 60.5. All right, half of that would be around 60.5 or so, and this is slightly less than that value. So the center of mass is pretty much somewhere in this region right over here. Okay, where I'm pointing to right there. That's where the center of mass of the system is. Again, it's really important to know where the center of mass of a system is when it comes to rotations, which we're going to get into in the next chapter or two. So we're learning about center of mass, but we're also going to use the concept of center of mass when we go into linear momentum. You know, we're going to linear momentum. Take a quick look. Well, I'll actually take an image of it, but I want you to take a quick look at page 219. So let's talk about this one. This is not a problem. This is more of an example that they're giving you here. So what they do is this. They say, what if we had an object that started as like, imagine a quarter, okay? Like a quarter, a coin. And from that quarter, you punched out a certain region of it. So let's say that the bottom circle, the bottom here is the full quarter. You take like, I don't know, what are those, the hole punchers? And imagine you could hole punch part of the quarter out. I know you can't, but let's say you could. You could hole punch a chunk of the quarter out. You take that out of the quarter. And now you've got that chunk here. What happens actually is this. The center of mass of the quarter without this part here slides over to the right. Because now more of the mass is concentrated on the right. The center of mass of this hole punched part is the center of it because it's still a circle. Now, what we'll notice is that the center of mass of this is far to the left. The center of this is just slightly to the right. But when we put them back together into the solid, the center of mass comes out to be right at the origin. Again, why is the center of mass at the origin here? Why isn't it like here, where it's between these two dotted lines? Because as soon as I punch out a portion of this, look at my center of masses. One is to the right of the origin, one is far to the left, yet the center of mass is now the origin again. How is that possible?
Is there still areas above and below the punched out circle that move the center of mass to the left?
The above and below actually only move the center of mass up or down.
Yeah, but they are to the left. The part above is still to the left.
What part above?
Like the hooks. I don't know how to describe
This
it.
portion, like here and up there?
Yeah, but further over, it's still.
Those would make me think, though, that the center of mass should be over here then, even further, the way you're stating that. My question, Tristan, is why isn't the center of mass here where you think it would be between the two center of masses of the two parts? Instead, it's not here, but it's shifted to the right, actually. Like, if I accounted for this, I would think it'd be shifted left more,
Yeah.
actually. But I'm saying it's actually to the right further.
Are they different weights?
Say again?
Since they're different weights, the bigger one with the hole cut out of it will affect the center.
Since they're different weights, masses, center mass. How would you know this is a different mass than this is?
It's the size.
And a quarter we know, or we think of a quarter or something like this. And think of this as even those slotted masses, right? Slotted masses. What do we know about them?
It's symmetrical.
Symmetrical, good. If they're intact like this, they're
Wait,
symmetrical.
actually, I don't know if it would be symmetrical.
Assume there's no hole in it, nothing like that.
Or
I
the
don't know.
design on the top of it.
Do they have a design?
Right.
Yes, quarter would have a slight design.
Well, what you were talking about earlier, it's like isotropic, so it's like the same throughout. And I have a question. Is like the reason why it doesn't move up or down because it's balanced on the y-axis, like an equal chunk is taken out?
On the top and bottom. Exactly
Yeah.
right. You hear what Chip just said? Why does the center of mass not move up or down? It only moves left to right, right? The center of mass of this guy just shifts left. The center of mass of this guy shifts right. But they don't shift up or down. It's because above and below the axis, it's still symmetry, right? There's symmetry here, and there's still symmetry of this guy above and below the axis. So there's no center of mass change this way. But this is not symmetric to this at all, right? Clearly? So the more of the mass is on the left side, so the center of mass is on the left for this one. For this one, more of the mass is on the right side, so the center of the mass slides to the right. So my question again, though, is like, why isn't the center of mass halfway between the dotted lines? Why isn't it halfway between the dotted lines? You're on the right track when you start saying mass.
Well, because like removing it doesn't, well, adding it back doesn't change the mass of the original object. So like, just because I don't know how to like articulate anything. It's like they're two separate objects, so they wouldn't necessarily have an average of an average center. So adding back the original mass would just make it the same as if it wasn't ever cut out.
So Matt's using the concept saying, put it back in, right? You'd be back to the original, and the original is definitely in the center, and you're right about that. But just extend on what you said a little more, Chris, because Chris had the right idea in the start, but just a little bit more than that.
The distance from the origin times the mass is the same as the
Good. The distance from the origin to the center of mass multiplied by that mass. So we're looking at this, ready? This distance right here times the mass of this entire thing. This distance right here, a lot bigger of a distance, right? Times the mass of this thing, which is a lot smaller of a mass. It turns out that they're going to balance each other. This is actually part of what we're going to talk about with torque also. This is a good lead-in into torque for the next chapter. And if you had me last year, I did a thing with like levers, like a seesaw. the bigger person could go a little bit further in, the smaller person has to go further out, and you can still get a balance, that kind of idea. The same concept is applied here with center of mass. So more of the mass for this guy is concentrated again here in the center and on the right side of this figure. Look at all this mass on the right side and this very little mass on the left side, which is why the center of mass on the right. This one's on the far left with a lot less mass than the other one has. So the red region clearly outweighs the green region up top. The yellow region outweighs pretty much nothing else that's there, which is why it's left. But the weighted average of these two gets you back to the origin. They get you back to the origin. All right, let me pause there just because I want to give you guys an open forum for some questions. Yeah?
Doesn't an ellipse have a center of mass?
Does an ellipse? Yeah, an ellipse will as well. Now, an ellipse doesn't have an actual center. It has what we call a major and a minor axis. But where those major and minor axes meet is the center of mass if the ellipse is isotropic, if it's made of an isotropic material. Because now we're talking about materials, right? So I'm not just talking about figures on a piece of paper, but ellipses exhibit vertical and horizontal symmetry, so the center of mass is definitely the center, assuming it's made out of the same material throughout. Okay?
So the two centers is just for when you're like graphing it or whatever?
The focal points, you mean?
Yeah.
Yeah, the focal points are useful for graphing and for a couple other things, actually, not just graphing. But the center of mass would be the average of the focal points, right, between them, assuming it's the same throughout. Okay, I'm going to stop today with this just to